to counting from this session onwards. One of the most important chapters of discrete mathematics is counting, because that is one of the most important things that we want you to learn to do in discrete mathematics. How to count things and how to identify similarities between seemingly different problems based on how you solve them by counting things. Okay, so we will discuss of some of the common procedures that we follow, some of the common rules that we use in order to solve problems that are relevant to counting. And by identifying those rules, what you are expected to do is identify similarities between problems. Once you do that, you can, if you are able to solve one problem, then you'd be able to solve all the problems which fall under the same category. And this is the concept that you will most often use. Counting and induction, I think these are the two things that you will most often use in proving algorithms or finding algorithms or finding the efficiency of an algorithm and stuff like that. All right. So counting is very, very important. So, the chapter of counting, it's very important that you understand all the concepts relevant to this chapter. Right. So let's just quickly delve into it. Okay. So in this session, we will deal with the basics of counting. We'll go over the product rule for this session, and in the next session we'll go over the sum rule, hopefully, and the basics of permutations and combinations as well in the second session, in the next session, that is, and that will cover the basics of counting, right? And from there we will go into more advanced concepts in counting. Okay, so let's get into it and talk about the product rule. When do we apply the product rule? We apply the product rule when there is a procedure that can be broken down into a set of tasks. And there are a number of ways to perform each of these tasks. And for each of the ways to perform, let's say, the first task, there are a number of ways to perform the second task, and each of the ways to perform the second task, there are a number of ways to perform the third task, and so on. If you have a scenario like that, there you apply the product rule. And how do you do that? How do you apply the product rule? Let's say, for example, you could break down the procedure into a sequence of two tasks. The procedure can be performed by performing these two tasks. So you can break down the procedure into a sequence of two tasks. And now each of these tasks can be performed in N1 and N2 ways, respectively. The first task can be performed in N1 ways, and for each of the ways to perform the first task, for each of these N1 ways to perform the first task, there are N2 ways to do the second task. If you have a scenario like that, then the total number of ways to perform the entire procedure is N1 multiplied by N2. Okay. Is that clear with everybody?
Yes, miss.
You sure? So if I just spring up an example on you, you'll be able to identify whether to apply the product rule or not and how to do it? Okay, I'm just messing with you. It's only understandable that some of you are not very, are still a bit foggy on this. I hope it will be clear by the time we do quite a bit of demonstration of the number of ways to apply the product rule. Okay. So the product rule, this is another application of product rule. Let's say you have to find out the total number of paths that come out of this junction. Okay. How would you do that? First, we have a set of 5 paths. Okay. You can take any one of these 5 paths. And for each of these 5 paths, whichever one you take, for each of them, you have 3 more paths to take. Okay. So ultimately, how many paths do you have at the end?
15, ma'am.
15, exactly. So if we broke down this entire procedure into 2 tasks, we could say that the first task is choosing a path among these 5. So how many ways are there to choose a path for the first task? How many ways are there to perform the first task? That is choosing a path. 5 ways. Yeah. And how many ways are there to perform the second task? What is the second task? Choosing a path. Again, after you've chosen one of the previous 5. How many ways are there to perform the second task? 3 for each of the paths that you take. All right? 3
Yes,
for
miss.
each of the paths that you take. The first task was choosing any one of these 5 paths. The second task is choosing any one of the 3 paths for each of the possible options that you had in the first task. For each of the ways to perform the first task, there are a number of ways to perform the second task. So you have n1 is equal to 5, n2 is equal to 3. Whichever path you take, after that you have 3 more paths to choose from. So for each of these options, for each of these ways, there are 3 more ways to choose from. 3 more paths to choose from. So in total, you have n1 multiplied by n2, as you can see here, pictorially as well. N1 multiplied by n2, which gives you 5 multiplied by 3 is equal to 15. And at the end, you do have 15 paths. So yeah, there you go. So that is one demonstration of the product rule. So in general, if you think about the product rule, if you have a procedure that can be broken down to any number of tasks, let's say it can be broken down into T1, T2, T3, and so on until Tm tasks in a total number of M. In a total of M number of tasks, you can break down the procedure into M number of tasks, denoted by T1, T2, T3, T4, Tm, and so on until Tm. And each of these tasks represented by Ti, where I represents the index again. I represents the index, which is a positive integer, which can have any value from 1 to m. I representing the index. So for each of these tasks, if each of these tasks can be done in any one of ni ways, again, I standing for the index, let's say T1 can be done in n1 ways, T2 can be done in n2 ways, and for each of the ways that you can perform T1 and T2, you can do T3 in n3 ways and so on. In that case, ultimately, the number of ways, the total number of ways you can perform the entire procedure would be the product of all of these sets of ways. n1 multiplied by n2 multiplied by n3 and so on until nm. There would be m factors, all right, here, and the product of all of the sets of ways would give you the total number of ways that you have to carry out the entire procedure, okay? So let's do an example. Here we are asked to find out the total number of license plates that could be formed where a license plate is constructed with a sequence of 3 uppercase English letters followed by 3 digits. So if you think about this process, you basically have to fill up 6 positions, right? In order to construct a license plate, 3 positions, the first 3 positions are for who? For uppercase English letter, the last 3 positions for digits. So in total, you have to fill up 6 positions in order to construct a license plate. So we could say that this procedure could be broken down into a sequence, into a series of 6 tasks of filling up the 6 positions. So what is the first task? The first task is filling up the first position. Now, the first position will be taken up by what? See, the first 3 positions would be uppercase English letters, and the last 3 positions would be 3 digits. So the first position, filling up the first position, that is our first task. What will be there in the first position? An uppercase English letter, all right? An uppercase English letter will be there in the first position. How many uppercase English letters are there? Guys?
26.
26. So how many options do you have to choose from in order to fill up the first position? 26 options, right? Makes sense so far for the first position?
Yes, miss.
Okay. Now, whichever uppercase letter you pick out of these 26 options, for the second position, you again have 26 options, right? Why? Because the second position is also going to be filled up by an uppercase English letter. The third task, which is filling up the third position, again for that one, uppercase English letter, so 26 options. All right. Now for the third position, sorry, the fourth position, Now for the fourth position. In the fourth position, again, will we have an uppercase English letter?
Digit.
We'll have a digit. And how many digits are there?
From 0 to 9, 10.
Exactly, 10. So you have 10 options to fill up the fourth position. Again, you have 10 options to fill up the fifth position, and same for sixth. Okay. So each of these tasks, from task 1 to task 6, can be performed in a set of ways. The first three tasks can be performed in 26, 26, 26 ways. The last 3 tasks, filling up the last 3 positions, can be performed in 10, 10, 10 ways. Okay. Also, on top of that, for the number of ways to perform the first task, which is 26, for each of these 26 ways to perform the first task, for each of those, there are 26 ways to perform the second task. Why am I using the expression for each of those? Think about it. Think about all the combinations. For the first position, if you pick A, for that choice, for that one choice, for A, how many options do you have for the second task? You have 26 options. For the first position fixed at A, then for the second task, you could either pick A, which makes the first and second positions AA, or pick B, AB, or pick C, AC, and D, and so on. All right. Now, instead of A, for the first position, if you picked B, you could have BA, BB, BC, BD, and so on. I'm talking about the first 2 positions. All right. So if the first position is taken up by A, then for the second position, how many options do you have? You have 26. For A, for just one option, for one choice that you made for the first position or the first task, there are 26 ways for that one way. If you pick A, you could have AA, AB, AC, AD, AE, and so on until Z. If you picked B instead, if you made that choice for the first task, if you performed it by picking the alphabet B, the uppercase letter of B, then you could have BA, BB, BC, and so on until Z. Same goes for C. If you picked C for the first position, then CA, CD, and so on. I'm talking about the first 2 positions. So you see that the 26 options that you had for the first position, for each of these 26 ways, for each of these 26 alphabets, there are 26 alphabets for the second position. For each of the 26 alphabets or 26 uppercase letters in the second position, there are 26 uppercase letters in the third position. For each of those ways to perform the third task, each of those 26 ways to perform the third task, there are 10 ways to perform the fourth task, and so on. All right. So you see, that's why we have to apply the product rule here. First of all, you had a procedure. You broke it down to 6 tasks, and we see that then we found out how many ways are there to perform each of these tasks, and then we established that for each of the ways to perform the first task, there are a set of ways to perform the second task. For each of the ways to perform the second task, there are a set of ways to perform the third task. We established that relation as well, and hence we can apply the product rule here, and hence the total number of many different license plates that you could have based on the given rules would be 26 multiplied by 26 multiplied by 26 for the first 3 tasks, and then 10 multiplied by 10 multiplied by 10 with the result of the first 3. Okay, so basically 26 multiplied by 26 multiplied by 26, then 10 multiplied by 10 multiplied by 10. So 26 to the power of 3 multiplied by 10 to the power of 3. Okay, does this example make sense to everybody? Any questions as to the solution of the example, as to how we applied the product rule here? Any questions?
No, ma'am.
Okay, all right, good. So what you need to remember here is the way we have identified that the product rule is applicable here. First of all, we had a procedure which could be broken down into a sequence of tasks, a sequence of filling up 6 positions. And then for each of those positions, we found out how many ways are there to fill up each of these positions. Then we established that, okay, for each of these 26 options, there are 26 options yet again to do the second task. So 26 multiplied by 26. For each of these 26 options to do the second task, there are 26 other options. So 26 multiplied by 26 multiplied by 26, and then so on. So that's how you do it. So we will do the same thing for functions, okay? So let me just quickly go over the slide for function to jog your memories a little bit. Okay. So, all right, before that, so basically what we want to do is we want to find out the total number of functions that are out there from a set with m elements to a set with n elements. That is a domain that has m number of elements and a codomain that has n number of elements. For such a situation, how many functions are there where m and n both are positive integers? Okay. Now let's look at this example. This was an example of a function, right? How many elements do you have in the domain here?
Miss 3.
In the codomain as well, we have 3 elements. Domain and codomain both have 3 elements. Now, this is one function from a domain with 3 elements to a codomain with 3 elements. But is this the only function that you could build from this domain to this codomain?
No, miss.
There could be a different way of mapping these things. Okay, as long as you follow the rules, you could have come up with many other functions for the same domain and codomain. Okay, now, okay, why is that? Let's get into it. Or how do we do that? How do we count the number of functions that are possible to be constructed from this domain to this codomain? Now, the first element, for the first element of the domain, here it's mapped to B. However, if you disregard that and if you think about the possibilities of the mappings of this element, the first element of the domain, how many possibilities are there?
3.
3. Very good. Because one could be mapped to either A or B or C. Either one of the elements from the domain. One could be mapped with either one of the elements of the codomain. So there are 3 ways to map the first element. Okay? Everybody with me so far?
Yes, miss.
Okay.
Yes.
All right. In that case, for each of these ways of mapping the first element, how many ways are there to map the second element?
Miss 8.
3. 3.
Miss.
Right? It's still 3. Remember, it's a function. You don't have to build a one-to-one function. So one of you, I think, said 2 ways.
Ma'am,
yeah.
আমি ওই যে প্রথমটা কানেক্ট করলে তার দুইটা বাকি থাকে সো আমি ওভার
Yeah. However, if you remember, this is a function as well, is it not? Fahim.
Yes, ma'am. Yes, ma'am.
See, 2 elements map to the same element of the codomain. See,
Yes,
we are
ma'am.
talking about function. If we were talking about one-to-one functions, then this wouldn't be allowed. However, just for simply functions, it's fine. So for the second element as well, we have 3 options to map the second element. So there are basically 3 ways to perform the second task. That is 3 ways to map the second element. How many ways are there to perform the third task? The third task being mapping the third element.
Miss 3.
3, exactly. So this entire procedure, we have broken it down to 3 tasks, basically, because that is what we do in function, right? We map each and every one of the element of the domain to exactly one element of the codomain, right? So here we have 3 elements in the domain. We have to map each of them. So we break down the entire procedure into 3 tasks, mapping the first element, the second element, the third element. The first element can be mapped to either one of the 3 elements in the codomain. The second element can also be mapped to either one of the elements in the codomain. The third element can also be mapped to either one of the elements in the codomain. So 3, 3, 3. 3 ways to perform the first task, 3 ways to perform the second task, 3 ways to perform the third task. So far, does it make sense, guys?
Yes, ma'am.
Okay. Now, also focus on the fact that for each of the ways to perform the three tasks, for each of the ways to perform the first task, for each of the ways to perform the first task, you have 3 ways to perform the second task. Why am I saying this again? For each of the ways to perform the first task? Because in order to be able to count all possible functions that can be formed from this domain to this codomain, you have to think about all possible combinations of the mappings, right? So for the first element 1, you could map it to either A, B, C. If you mapped it to A, for that mapping from 1 to A, 1A, for that mapping, you could map 2 to A, B, or C. So already you could have 3 functions. 1 map to A. I'm just focusing on the first 2 elements for now. 1 map to A, and then 2 map to A, that gives you 1 function. Then 1 map to A, 2 map to B gives you another function, and 2 map to C gives you another function. Then if you map 1 to B, for that mapping, again, you have 3 more possibilities with 2, okay? If you map 1 to B, then again, 1 to B and 2 to A, 1 to B and 2 to B, 1 to B and 2 to C. So 3 more functions. And if you map 1 to C, again, for that one, you count the number of ways. You can map 2, all right? So you see why I'm saying over and over again that for each of the ways to perform the first task, for each of them, there are a number of ways to perform the second task, all right? That relation, that for each of the ways, each of the 3 ways to perform the first task, for each of the 3 ways to perform the first task, for each of them, you have 3 ways to perform the second task. And for each of the 3 ways to perform the second task, you have 3 ways to perform the third task. So we apply the product rule here. So the total number of functions from this domain to this codomain, the total number of functions that are possible to be constructed would be what? 3 multiplied by 3 multiplied by 3.
21.
All right. That is 3 cube. Okay. Does it make sense, guys?
Yes, miss.
Yes, ma'am.
Okay. Now let's think about what would happen if we had M for monkey, M number of elements in the domain, and N for N elements in the codomain. All right. If we had M elements in the domain and N elements in the codomain, what would happen then?
M to the power n.
M to the power of N. Are you sure about that? Before getting to that, let's just break it down, okay? So if we had M number of elements in the domain, and we want to break the entire procedure down, can we not break it down to a total of M number of tasks? M for monkey, that is. If you have M number of elements in the domain, we can break it down to M number of tasks, right? Because ultimately, what is the procedure? How do you form a function? Once you have mapped each and every element in the domain, right? You have a function in your hand once you have mapped each and every element in the domain to exactly one element from the codomain. So you have to map each and every element in the domain. If you have M elements in the domain, how many elements do we have to map, guys?
M number of elements.
M number of elements. So basically, we have to perform M number of tasks, where each of the tasks is mapping each of the elements. Okay? So let's say the first task is mapping the first element. For the first element, in order to map the first element, how many options are there to map the first element? Equivalent to the number of elements in the codomain. How many elements are there in the codomain? N. N number of elements. N for no. N number of elements in the codomain. So for the first element from the domain, how many possibilities are there to map the first element? How many options do you have?
N.
N, right? N. So for the first task, to perform the first task, you have N number of ways. And for each of these ways to map the first element, how many ways are there to map the second element? Still N. For the third one, again N, fourth one N, and so on, until the last task, which is the last task, that is the mth task, which is mapping the mth element. To map the mth element as well, you have n number of ways to do that because you still have n elements in the domain, okay, to map the function to. All right. So the total number of ways to perform the entire task, that is the total number of functions that you could have from a set with m elements to a set with n elements, would be what? The product of all of the ways, right? The product of all of the ways. For the first one, how many ways were there to perform the first task? That is map the first element. Guys, how many ways were there to map the first element here?
And
N. N.
Okay, yeah.
N. Why N? Because there are n elements in the codomain. For the first task, you had n ways. For the second task, how many ways were there to perform the second task, which is mapping the second element?
n again.
Still n. So n multiplied with n. For each of the ways to perform the first task, that is each of the n elements that we have as options for the mapping of the first element, there are n elements to choose from again for the second element. All right. So n multiplied by n. Then for each of the choices for the second element, there are n choices to map the third element. So n multiplied by n again. So n multiplied by n multiplied by n. And then for the fourth task as well, again n, so multiplied by n. And you will keep multiplying n until what point? Until you reach m. So you will multiply all the n's. And how many factors will be there? There will be m for monkey, m factors. All right. So what you would have is, in fact, n to the power of m, the opposite of what you said, n to the power of m. All right. So the number of ways to perform each of the tasks to the power of the total number of tasks that you have to perform. So for the first task, there are n ways. That is to map the first element. To map the first element, you have n options, that is n ways. To map the second element, again, you have n ways. The third element, n ways. Fourth element, n ways, and so on until the mth element, for which again you have n ways. So you will multiply all of the n's. There will be m factors. So n to the power of m functions out there from the set of m elements to the set of n elements. Is this clear to everybody?
Yes, yes.
Okay, if this is clear to everybody, let's do the same thing for one-to-one functions this time. Okay, before that, let's just brush up on one-to-one functions. Is this a one-to-one function, guys? Is this an example of a one-to-one function?
Okay. Yes.
Yes.
Yes, this is a one-to-one function. Is this an example of a one-to-one function? This one? No, it's not. Okay. So a one-to-one function, there, each of the elements of the domain are mapped to a unique element of the codomain, right? So that's why this is a one-to-one function. This is not a one-to-one function. What about this one, though? Is this a one-to-one function?
Yes.
Yes, it is also a one-to-one function. This one is also a one-to-one function. Each of the elements are mapped to unique elements. Okay, so this is a one-to-one function. Okay, why is this not a one-to-one function? Because the number of elements in the domain is greater than the number of elements in the codomain. So obviously, at one point or the other, you would have to map multiple elements from the domain to the same element in the codomain. All right. So if you wanted to do the same problem for one-to-one functions, that is, find out the number of one-to-one functions from the set of m elements to the set of n elements, where m and n are positive integers, there has to be another condition on top of that. What is that? That m cannot be greater than n. M is the number of elements in the domain. N is the number of elements in the codomain. If the number of elements in the domain is greater than the number of elements in the codomain, what does that mean? At one point or the other, you would have to map multiple elements to the same elements, that you wouldn't have unique mappings for each of the elements. So if m is greater than n, then there wouldn't be any one-to-one functions at all. Okay? There wouldn't be any one-to-one functions at all if m were greater than n. So in order for this to work, M and N have to be positive integers. Yeah, sure. Also, on top of that, M has to be less than or equal to N in order for us to have any one-to-one function at all. M has to be less than or equal to N. That is, the number of elements in the domain has to be less than the number of elements in the codomain, or has to be equal to the number of elements in the codomain. Otherwise, it will not be a one-to-one function. Okay. So yeah, assuming that M and N are both positive integers and M is less than or equal to N, that is, M is not greater than N. Assuming that, let's try to find out the number of one-to-one functions that could be formed where the domain has M elements and the codomain has N elements. Okay. Now, if you had to form a one-to-one function here, again, let's break it down to 3 tasks. Okay. The 3 tasks of mapping each of the 3 elements. Okay. 3 tasks of mapping each of the 3 elements. So for the first task is what? Mapping the first element. Yeah. So to map the first element, how many options do you have?
3.
You have 3 elements to choose from. You have 3 elements in the codomain to choose from. Fine. And for each of those ways to perform the first task, once you have performed the first task, you have already chosen an element. Bear that in mind. Once you have performed the first task, you have chosen an element, and for each of those choices, once you have made the choice, how many options do you have left for the second task?
2.
What is the second task? Mapping the second element. Once you have mapped the first element to one of the elements from the codomain, how many options are there for you to map the second element?
2.
2. Why is that?
Because it is a one function, and we have to select one.
It is a one-to-one function, yes, and whichever element we picked for mapping the first element, that cannot be chosen again. The element that we chose to map the first element, the element from the codomain, the one that we picked, that cannot be picked once again because every mapping has to be unique. Yeah? So, yes, you're correct. For the second element, we have 2 options left. For the third one, how many options would be left?
1.
Just 1. So, the total number of one-to-one functions, that you could have from this set to this set would be what? 3 multiplied by 2 multiplied by 1, right? 3 factorial. Okay. For this example, for the first element, how many options do you have?
3.
For the second one?
2.
So there are 3 ways to perform the first task basically and 2 ways to perform the second task. So how many possible functions are there from this set to this set? 3 multiplied by 2. So you see there's a pattern here. There's a pattern here, all right? So let's say if we had m number of elements in the domain and n number of elements in the codomain, now let's consider that generic case, all right? For m number of elements in the domain and n number of elements in the codomain, for the first task, which is mapping the first element, we have n ways to do it, right? N ways to do it. Now, for the second task, which is mapping the second element, how many ways would you have left? N minus 1, exactly. It's a one-to-one function, right? So first element, you have n ways to choose the mapping of the first element. But once you have chosen that, you have already picked one of the options. So the elements that are left for the second mapping would be n minus 1 because you've already chosen one of the options. You have already chosen one of the mapping. So for each of the ways to perform the first task, that is, for each of the options we have to map the first element, there are n minus 1 ways to map the second element. For each of the n ways to map the first element, there are n minus 1 ways to map the second element. Now, for each of the n minus 1 ways to map the second element, how many ways would be there to map the third element. Remember, so far, how many elements have you picked? Sorry, or how many mappings have you done so far?
Two.
Two. So you have already picked 2 elements from the codomain. Can you pick those 2 again?
No, miss.
No. So for the third element, how many options do we have?
One.
Remember, we are assuming a scenario where there are total
N
of
minus
n elements in the codomain. If you had in total n elements,
N minus 2.
n minus 2. For the third mapping, you have n minus 2 options. For the fourth, for mapping the fourth element, you would have how many options?
N minus 3.
N minus 3. Because once you get to the fourth element, you have already mapped the previous 3 elements, right? So if you have mapped the previous 3 elements, you've already chosen 3 elements from the codomain. So for the fourth element, you have n minus 3 choices. For the fifth element, you have n minus 4 choices, and so on. Okay? Until you get to the mth element. The mth element from the domain. The mth element, that is the last element from the domain. For that element, think about it. Once you get to that element, once you get to the mth element, so far, how many elements have you mapped?
M elements.
M minus 1.
Yes, miss.
Once you get to the mth element, before that, you've already mapped m minus 1 elements. Right? So if you have mapped m minus 1 elements, that means what? You have already picked out m for monkey, m minus 1 elements from the codomain. In the codomain, you had a total of n elements, n for no, all right? In the codomain, you had a total of n elements, and from those n elements, you picked out m minus 1 elements already before you got to m. Make sense, guys?
Yes, miss.
So in that case, for the mth element, for the last element, how many options do you have?
N minus M plus 1.
Exactly, very good. N minus m plus 1. How? You have total n elements in the codomain, and once you get to m, it means that you've already picked m minus 1 elements from the codomain. You cannot choose those m minus 1 elements again. So n minus what? N minus that many elements. N minus the m minus 1 number of elements. So n minus m minus 1 gives you what? M minus 1 is in parentheses, right? So n minus m plus 1. So yeah. So yeah. Given that m and n are positive integers and m is less than or equal to n, to pick the first element, there are n ways. To pick the second element, there are n minus 1 ways. To assign the third element, there are n minus 2 ways, and so on. And to map the last element, the mth element, there are n minus m plus 1 ways. And for each of the ways to choose the element for the first mapping, each of the n ways to choose the first element for the first mapping, there are n minus 1 ways to map the second element. And for each of those n minus 1 ways, there are n minus 2 ways to map the third element, and so on until the last element, for which we have n minus m plus 1. So finally, the total number of one-to-one functions from the set m to the set n, where m is less than or equal to n, and m and n are both positive integers, the total number of one-to-one functions would be n multiplied by n minus 1 multiplied by n minus 2, and so on until n minus m plus 1. Okay? Any questions regarding this example? Okay.
No.
All right. In that case, you guys try to solve this. How many different bit strings of length 7 are there? First of all, think about the procedure that you have to perform, or the main task that you have to perform, and if it can be broken down into smaller tasks or not. The procedure is to find out or construct, all the possible bit strings of length 7.
Miss,
Come again?
what are bit strings?
We've discussed bit strings in the previous sessions. Remember, bit strings are strings composed of bits. And what are bits? A bit is either the value 0, or I can either take the value 0 or 1.
Okay, miss.
So bit strings are strings that are composed of only zeros and ones, okay? For example, in the truth table, you saw the combination 00011011, right?
Yes, yes.
Each of those four are bit strings. 00 is a bit string, 01 is a bit string, 10 is a bit string, 11 is also a bit string. Okay? Each of those are bit strings of length 2. So remember, is it clear now? Can you remember what bit strings were?
Yes, yes.
Okay, very good then. So in that case, let's see how we can do this. This procedure, let's see if we can break it down to a sequence of tasks. Okay, so we have to construct all the possible bit strings of length 7. If it's of length 7, what does that mean? How many positions do we have to fill up?
7.
7. So basically, we can break down this entire procedure, this entire task, into 7 smaller tasks, filling up each of those 7 positions. Okay, so that's one. We've broken down the task or the procedure into 7 smaller tasks. Okay, now let's go task by task. The first task is what? Filling up the first position, yeah? Now for the first position, it's a bit string, remember? It's a bit string, a string that's composed of only bits, and a bit is either 0 or 1. So for the first task, which is filling up the first position, how many options do you have?
2.
No, ma'am.
2.
2, exactly 2. Why? Because the first position can either be 0 or 1. So the number of ways to perform the first task is 2. What are the number of ways to perform the second task? That is filling up the second position.
2 again.
2 again.
2 again.
And for each of these ways to perform the second task, how many ways are there to perform the third task? 2 again.
Yes, yes.
And
2 to the power 7.
So, very good. 2 to the power of 7. The total number of different bit strings of length 7 would be 2 to the power of 7. We've broken down, see again, we have broken down the entire procedure into a sequence of 7 tasks where each of the tasks can be performed in any one of 2 ways. And also note that for each of the 2 ways to perform the first task, for each of the 2 ways to perform the first task, there are 2 ways to fill up the second position, that is perform the second task, and so on. All right. So you have to think about all possible combinations. If there was a bit string of, let's say, length 2 er bit string ta bolam 00011011. How did we get there? 0001. What did we do there? Think about it. Truth table is 0001. Ki korchi ekhane? We picked 0, and then for that 0, we have the option of choosing 0 or 1 for the second position. If you pick 1 in the first position, for that choice, you have 0 or 1 for the second position. So you see, for each of the choices that you make for the first position, you have 2 choices for the second position. For each of the choices that you make for the second position, you have 2 choices for the third position, so on until the 7th position, basically. So we can apply the product rule here, 2 to the power of 7, which gives us 128 different bit strings of length 7. Make sense, guys?
Yes, miss.
Okay. In that case, let's move on to the idea of a Cartesian product. So let's say we have any set A to the power of n, where n is an integer, a positive integer greater than or equal to 2. A to the power of n represents what? The Cartesian product of the set A with itself over and over again. And how many times would we do that? N times. So A, Cartesian product with A, Cartesian product with A, so on for n factors. Okay. So what we will do is we will show you that it is possible to find out the size of a Cartesian product by applying the product rule. That is, the size of the Cartesian product is found, the formula for that is found using the product rule indeed. Okay. So before that, let's just go back to our concept of Cartesian product in set theory. Okay, where was this again? Okay. So remember this example of Cartesian product between the set A and set B. How did we do this? We picked first the first element of the first set. We picked the first element of the first set, which was 1. And for this choice, how many choices did we have from B? A, B, C. For the first element that we picked from the first set, for that one, we had 3 choices from B, A, B, C. Why 3? Because the number of elements in B is 3. And then we picked the second element from A. We picked the second element from the first set. And for that choice, again, we had 3 options to choose from for B, A, B, C. And we went with A, B, C. So you see, what we're doing here basically is picking an element from the first set and an element from the second set. Every time we are constructing a tuple for the Cartesian product. We're picking an element from the first set, and for that choice, we're picking an element for the second set. So how many ways are there to pick an element from the first set? What do you think? How many ways are there to pick an element from the first set?
2.
2. Why is that? Because there are 2 elements in the first set. You have 1 and 2. So you can pick either one of these 2 only. So you have 2 ways to perform the first task. You have 2 ways to perform the first task, which is picking an element of the first set. And as you can see here, for each of these choices, if you pick 1 for that choice, how many ways are there? Once you choose 1, how many ways are there to choose an element from B?
3.
3, exactly, because there are 3 elements in B. So you can, once you have picked 1, you can go with 1A, 1B, and 1C. Then once you've picked 2, for that choice as well, you have 3 options, 3 ways to perform the second task. That is 3 options to choose for the element of B from B. So for each of the 2 ways to pick an element from set A, there are 3 ways to pick an element from set B. For each of the 2 ways, for each of them, by the way, for each of them, there are 3 ways to perform the second task, which is choosing an element from B. So what would be the size of the Cartesian product then? You can find out the size by counting the number of ways to perform the first task and the number of ways to perform the second task. And we've also seen that for each of the ways to perform the first task, we have a set of ways to perform the second task in case of Cartesian product, as you can see here. So here, the size of A cross B, what is the size? Just count the number of elements here. 1, 2, 3, 4, 5, 6. We have 6 elements in the Cartesian product. So the size of the Cartesian product is 6. Okay. Also, you will see that if you apply the product rule, you will get to the same result. The number of ways to perform the first task, which is choosing an element from A, is 2. You said that. The number of ways to perform the second task, which is choosing an element from B, is 3. 2 multiplied by 3 is what? 6. Okay. But the procedure of constructing a Cartesian product, do you see the parallel between the procedure of constructing a Cartesian product and the product rule? The scenario where we apply the product rule. Do you see the similarities, the parallel between the two?
Yes, Miss, they're like the same.
Yeah, basically they're the same. We have to perform 2 tasks, that is, pick an element from A and an element from B. And for every choice of element of A, you have 3 choices of element from B. So product rule, you have 2 tasks, you have to perform 2 tasks, and you have 2 ways to perform the first task, 3 ways to perform the second task. And for each of these 2 ways to perform the first task, there are 3 ways to perform the second task. So 2 multiplied by 3. Okay. So now, in that case, let's talk about the generic situation. Generic situation. What happens when you have a number of sets, any number of sets, and you want to find the size of the Cartesian product of any number of sets? How do you do that? Let's say we have the sets A1, A2, A3, and so on until M. That is, we have a total number of M finite sets. Okay, A1 through AM, we have total number of M finite sets. Okay, now we have to find out the size of the Cartesian product between these sets from A1 through AM. Okay, we have to find out the Cartesian product. In order to find out the Cartesian product, just like we have done for this example, here we broke it down to the task of choosing an element from A and choosing an element from B, and we took it from there. Here, it's the same thing, isn't it? You want to find the size of the Cartesian product between A1, A2, A3, and so on until AM. How do we construct the Cartesian product? First, we choose an element from A1, right? And for that choice, for that specific choice, we choose an element from A2. For that specific choice, we choose an element from A3, and so on. And how many ways are there to choose an element from A1? Guys, how many ways are there, do you think, to choose an element from A1?
Number of elements of A1.
Exactly. The size of A1. The number of ways to choose an element from A1 is the size of A1. Okay? And for each of these ways, how many ways are there to choose an element from A2? The size of A2, the number of elements in A2. And for each of these ways, how many ways are there to choose an element from A3? The number of elements in A3, and so on until M. So you see, for A1, from A1, you can choose any one of the elements in A1, the size of A1, all right? And for each of those choices, for each of those choices of elements in A1, you have how many options to choose an element for A2? The size of A2, and so on. So if you understand that, then you should be able to see that the size of the Cartesian product of all of these sets would be equivalent to the product of the size of each of these sets individually. The number of ways to choose an element from A1 is the cardinality, or the size of A1, the number of elements in A1. And for each of the options that you have to pick an element from A1, for each of the ways to perform the first task, for each of those, you have a set of ways, a number of ways to choose an element from A2, which is equivalent to the size of A2 again, and so on until AN. So the size of the entire Cartesian product would be equivalent to the product of the size of all the sets in the product individually. Okay? So you see, this directly follows from the product rule. Can everybody see the similarity? Is this clear to everybody?
Yes.
Okay, no questions then. Good. Was there a question? I couldn't hear. Sorry, there was a lot of noise or interference. Was there a question, guys? Okay. All right, then. In that case, let's move on. We will also now find the number of subsets of a finite set by applying the ideas of product rule. And one other idea that we've already established, okay? The number of subsets of a finite set. Let's say S is that finite set. We have to find out the number of subsets of this set S. Okay. So the way we can apply the product rule here, the way we can do that, or the reason we can apply the product rule here, is because there is a parallel between the number of subsets of a finite set and, let's say, the number of subsets of a set that has n elements, the number of subsets of a set that has n elements, and the number of combinations that you have. Okay, so the number of sets subsets that you would have from a set that has n elements and the number of possible combinations in a truth table for n variables, there is a parallel between the two. Okay, we've actually talked about this a little bit when we were discussing subsets and the number of subsets, that is power sets in set theory. When we were discussing power sets, I mentioned just in short, I just mentioned that the fact that the number of subsets of a set with n elements is 2 to the power of n, that comes from the fact that there is a parallel between the number of subsets of a set with n elements and the number of possible truth combinations for n variables. All right. Okay. Let's just first see what a power set was, just to brush up your idea on that. Okay, yeah, here. So remember here, A is this set, right? A is the set that contains 0, 1, 2. What are all the subsets that you can have of A? The empty set, the set containing 0, 1, 2, and so on, all right? You could have all of these sets, all of these subsets of A, right? These are all the possible subsets of A, which are there as elements of the power set. Remember that we said that the size of a power set would be 2 to the power of n for a set with n elements, because there is a parallel between bit strings and this. We'll just establish that, okay? So the way we will represent the sets and the subsets and the corresponding subsets is we will use a bit string of the same length of the set itself, all right? So here we have a set S. We have a set S. We have a finite set S. Let's say S has a number of elements, okay? There is a one-to-one correspondence between the total number of subsets of S and the total number of bit strings which have a length equivalent to the size of S. That is, the number of elements in S is equivalent to the length of the bit string. If the number of elements is equivalent to the length of the bit string, in that case, how many bits would you have in these bit strings? How many bits would you have, guys? If it's equivalent to the length of S, how many bits would you have?
Miss S,
S or the number of elements of S?
number of elements.
But the number of bit strings in this bit string would be equivalent to the number of elements in S, all right? So there is a one-to-one correspondence between the total number of subsets of S and the total number of bit strings of length S, all right? How so? We can represent all subsets of S using bit strings. If you represent the set S, if you represent the set S as a bit string, as some bit string, if you arrange the elements of the set S in some arbitrary order, whatever you want, whatever order you want, you set them in some arbitrary order and keep them that way, and represent the set S using a bit string. In that case, its subsets can also be represented using a bit string. How so? The ith position of the bit string, the ith position of the corresponding bit string, which represents the subset of S, the ith position of the bit string will take the value of 1 if the element in the same position in the set S is there in the subset, and it will take 0 if the element in the same position in the set is not there in the subset. All right? Make sense?
Basic to what?
Ma'am, could you repeat the last part?
Okay. Yes, of course I can. So yeah, thank you for asking the question. So what we can do, I guess, is demonstrate it a little bit, and then it'll be clearer, I hope. Okay, let's say we have a set S, okay, which contains the elements A, B, C, D. Yeah. Let's say we are representing it with a bit string B, 1, 1, 1. Okay. What we are saying is that for every subset of this set, we will represent it with a bit string that has the length, a length equivalent to the size of this set. the size of this set is 4. The length of the bit string will be 4 as well, as you can see. So let's say the subset S1 of this set contains the element A and C. If it contains A and C, this is a subset of S, right? Is that part clear? Is that bit clear that this is a subset of S?
Yes, miss.
Okay. So we represent this with a corresponding bit string. Okay. We represent this with a corresponding bit string where we have 1 in the first position. Why? Why do we have 1 in the first position? What element do we have in the first position of S?
A.
A, exactly. Is A there in the subset?
Yes, miss.
Yes. If it's there, in that position, in A's position, we will have 1. Okay. Which one is the second element in S?
B.
B. The element in the second position is B. Is B there in the subset?
No.
No. So we will use a 0 for the second position in the bit string because the second element is not theirs. What is the third element? C. As you can see, C is here. So correspondingly, what will be there in the third position of the bit string?
1.
1. Because in the third position we have C and C is there in the subset. So the third position will take the value of 1. And the fourth position has a value of 0. As you can see here. Why? Why do we have 0 here, guys? In the fourth position?
We don't have any element in the subset.
Sorry?
We don't have any elements in the subset.
We don't.
Which
We do have elements in the subset with AC, but we do not have the element in the fourth position, to be exact. We don't have D in the subset, and D is in the fourth position. That's why we have 0 here. Okay? So that is how you can represent the subsets of the set using a bit string. Okay? So you see, this bit string has a meaning. When you see 1, you should be able to tell that, okay, the element in the first position would be there in the subset. If you see 0, it means that the element in the second position is not going to be there in the subset, and so on. Okay. Similarly, S2, which represents the set AD. AD is a subset of this set, right? AD is a subset of this set. So the corresponding bit string would be 1001. Why is that? Because in the first position we have A, and A is there in this set. So 1 for that. And in the second position we have B, and the third position has C. The second and third elements, B and C, are not there in this set. So the second and third positions are 0. And the last element, D, is there in this set. So the last position is taken by 1. Is it clear to everybody?
Yes, sir.
Okay. What about this?
0, 0, 0, 0.
Very good. Exactly. I have 0, 0, 0, 0 here.
Miss, S3 is the subset, right?
Sorry?
S3.
3 what again?
Is it a null set?
Yes. S3 is a null set. And the null set is a subset of all sets, right? Remember?
Yes.
Yeah. And S also, remember, is a subset of itself. Yeah?
Yes.
So this bit string represents who? Represents this set itself, which is a subset of itself. So you see, the bit strings can be used to represent all possible subsets of this set. Yeah?
Yes, miss.
So all possible combinations of these 4 bits in this bit string represent all possible subsets of this set. Yeah? So for this specific set, how many subsets would there be for this specific set? For this specific set, this one, how many subsets would there be? What do you think? Think about it. Think about the bit strings that we are using to represent them. The bit string represent each of the subsets, right? All possible combinations in the bit string represent all possible subsets of this set.
Miss 2 to the power
2 to the power of 4, exactly. Correct. 2 to the power of 4. That is correct. The length of the bit string is 4. If you have 4 bits here, you have 2 to the power of 4 possibilities. We established that already, right? Where did we establish that? Establish that here, right here, sorry. Yeah, here. We established that in this example. Yeah. At a bit string of length n, for that bit string, you'd have 2 to the power of n combinations by applying the product rule. We applied the product rule to get here. Now that we know this, that we know that by applying the product rule, we can establish something like this. If we draw a parallel between the bit string and the number of finite sets, the number of subsets of a finite set, in that case, we can say that the number of subsets of a set is equivalent to the total number of bit string that can be formed, which is of the length of the that is the same as the size of the set. All right. So the size of the set is 4. The length of this bit string is 4. The total number of bit strings that are possible to be constructed that has the length 4 would be 2 to the power of 4. We've already established that in that example involving 7 bit strings. Sorry, a bit string of length 7. Based on that example, you should know that if a bit string has length 4, then the total number of bit strings that can be formed for a bit string which has the length 4 would be 2 to the power of 4. And hence, if you draw this parallel, we can say that the number of subsets of this set, which has 4 elements, would be the same, 2 to the power of 4. Right?
Yes, yes.
Okay.
Using like bit strings, it is easier to find number of subsets. I mean, power set.
Come again? Sorry, there was a lot of interference. I mean, you were breaking up. Yeah, go ahead again, Fahim.
Means to find the power set, it is easier to get bit strings. Like in this way. You can just size and
the power set to
Yes,
find the size of the power set. Yeah, the size of the power set. Remember here in the set theory, we just established that we just basically just simply mentioned and went on that the size of the power set of a set with n elements would be 2 to the power of n. But why or how? How do we establish that? We establish that by counting the number of subsets of a finite set in this way. That is, finding a parallel between the number of subsets of a set and the number of bit strings of length that is the same as the size of the set of the given set. There is a one-to-one correspondence between the two. The way we've just shown that a subset of S would be associated with a certain bit string with a 1 in the ith position if the ith element, if the element in that specific position in the set S is there in the subset as well. If it's there, then it will be 1. If it's not there, it will be 0. Okay? Just like we've done it here. Okay? So if you do that, if there's a one-to-one correspondence between the two, it means what? The number of bit strings that you can form of this length is the same as the number of sets, the number of subsets that you would have of this set that has the same number of elements. Okay? Because all of these bit strings represent what, basically? All the bit strings that has length 4 represents all possible subsets of this set, right? So since there is a one-to-one correspondence between the two, we can say that by the product rule, there are 2 to the power of the size of S, 2 to the power of the number of elements of S, bit strings of length equivalent to the size of S. That is, in other words, the power set, the length, the size of the power set of S would be 2 to the power of the size of S. Okay? Is this clear to everybody? Any confusion left? If there are any confusion left, you can go ahead and ask instead of being quiet. Okay? All right. So if you understand that, this is just another way of expressing the same thing. This is the exact same approach, by the way. See, alpha I represents 1 or 0 for AI present in A and AI not present in A, respectively. 1 for AI present in A, 0 for AI not present in A, right? So this is the same, exact same approach that we followed here. This is just written down in a different way, using notations that we've studied so far, set notations, logic notations, all of those notations that we've studied so far. This is a formal proof, basically. This is a formal proof of the fact that the number of subsets of a finite set would be 2 to the power of n if the size of the set is n. Okay, this is a formal proof of that. What we have just discussed here is the exact same thing that they're saying here. This is written in a different way. Okay, so go over this proof in your free time and see if there are any issues with it. There shouldn't be any, because this is the exact same thing that we've studied here. If in the exam, if you come across something like this, you can explain it in this way or explain it in this way. Either one is fine, as long as you lay down your logic by covering every single step. Okay, this one is definitely more preferred, but at your level, I wouldn't push you that far. So yeah, you can, as long as you even explain it in this way, that's fine. But still, go over this in order to get an idea about how to write a formal proof. Okay, but it's the same idea. It's the exact same approach as this one. Okay, so let's end the session here. From the next session, we will pick up from some rule. All right, we'll pick up from some rule in the next session. And I'll end the recording here.